All right, so everyone, thanks for attending our session today. Avi and I are super excited to spend some time with you today exploring the use of AMD GPUs and the Databricks platform for pre-training, fine-tuning, and inference of generative AI models. So we're going to give you a quick overview of AMD hardware and software. We're going to show you how to use AMD at scale for pre-training large models, and then we'll get into showing you how to transfer these models between a GPU cluster environment over to the Databricks platform. And finally, Avi will take you through fine-tuning and hosting these models on Databricks. So let's get started with some introductions. I'm Keith Anderson. I'm a senior member of technical staff at AMD. I work in the data center GPU cluster solutions organization. And my role lately is focusing on automation and tooling for running AI workloads on large GPU clusters. Turn it over to Avi to do his intro.
Great, thanks, Keith. So I'm Avi Sirarachi. I'm a solutions architect at Databricks. I've been here for close to 3 years, and I primarily focus on machine learning, mostly deep learning, and as of late, like everybody else, focus mostly on getting customers to build things with large language models, things of that nature. So excited to present to you.
Cool. So I'm sure many of you are here, hopefully, because you're curious about where AMD stands in kind of the 2024 GPU market and how we're positioning ourselves in the industry that's long been dominated by a single GPU vendor. So my goal today in the first half of the presentation is to show you that AMD is ready to run your heaviest GPU workloads. And I'll walk you through an example of pre-training a GPT model from scratch on a few servers using AMD hardware and software. So you might be wondering, is that going to involve me refactoring all my code? How heavy of a lift is it to use AMD for my training? Short answer, not at all. All of your ML frameworks will work out of the box on AMD hardware and software. So for example, all of your PyTorch code will run very easily as long as you just install the package with AMD support. So we'll walk you through the kind of the state of the union on AMD hardware and software. So if you've got private data sets that you don't want to put in the cloud, you can build out a GPU cluster on-prem with a fast RDMA network in your data center. If you prefer the cloud, our latest MI300X GPU is now available in Azure as an instance and includes InfiniBand networking as well for multi-host workloads. So once you've built out an AI model, we'll get into the second half of the presentation where we'll move that model into the Databricks platform, where you'll have the tooling to manage your models, your data sets, fine-tune the model, and run inference for your applications. So if you're running heavy GPU workloads, combining AMD hardware and software plus the Databricks platform gives you a great end-to-end solution from pre-training all the way to model hosting. So how do we do this? How do we build a large LLM from scratch and then move it over to Databricks for our applications? First thing, we'll just need to take a step back and decide, do we want to pre-train a model or do we want to just buy a model? Buying a model is just kind of paying a model provider for API access to a foundational model, or maybe even downloading model weights and maybe doing some fine-tuning on a foundational model. But building a model from scratch means kind of building up an environment and implementing a model architecture in your code. So this does not involve any model weights. So you're not going to be downloading a foundational model. You're actually building it from the ground up with code. And since we're focusing on pre-training a model from scratch today, let's kind of talk about why you would pre-train one. So you might expect building your own model may potentially give you better performance, but just as important, you can get more control over a model's behavior, especially if you're using some proprietary data and it's specific to your horizontal or vertical use cases. So in this case, you wouldn't necessarily want to just download the same foundational model as your competitors, especially if this is going to impact your revenue. So Making an investment in pre-training a model from scratch can help pay off, especially if this is something that's going to impact the bottom line of your business. So let's assume that you do go ahead and pre-train your own model on-prem or in the cloud. Moving this model to Databricks becomes pretty easy. Once you want to run some fine-tuning and inference, the model weights can be large, it can be up to a couple hundred gigabytes, so that might be tricky moving the model weights around, but Databricks has tools like Delta Sharing and Unity Catalog that can make this a lot easier. Once you move this to the Databricks platform, you can fine-tune and run inference. So this gives your MLOps team a cloud platform to manage your models and manage the hosting, manage the fine-tuning. So just to sum up, pre-training your own model gives you more granular control and customization over your model, which can give you a business advantage. And once you've moved this model to Databricks, the fine-tuning and inference are a lot easier using that platform. Okay, so I'm going to take a few minutes to just give an overview of the latest AMD GPU offerings, and then we'll get into pre-training a model from scratch on a GPU cluster. So at a high level, I'm just going to talk in three broad categories: the hardware, the software, and kind of the ecosystem for training a model on a GPU cluster on AMD. So late last year, we released our latest hardware, the MI300X. This is part of our Instinct line of GPU accelerators. For those who follow the specs, this is 1.3 petaflops of bfloat 16, and it also gives you 1.5 terabytes of GPU memory. In Linux, the MI300X appears as 8 logical GPUs. So these are aggregate benchmarks, and this also gives you a combined bandwidth of about 900 gigabytes a second using XGMI connectivity between these 8 GPUs, which I'll talk about in a few minutes. I mentioned you can run these in Azure. This GPU is now available in Azure as the ND MI300X v5 instance type. So this means you can rent a pretty powerful VM with an entire MI300X. And if you're using more than one instance, this also comes with a 400 gigabit InfiniBand network for connectivity between these Azure VMs. Let's next talk about the software that runs these GPUs. You've heard me mention ROCm. This is the open source code that we use for the drivers and the associated software that powers our GPUs. The software gives you tools for traditional HPC type workloads along with more AI-focused functionality for working with the latest machine learning frameworks. The ROCm software is the same, whether you run data center Instinct GPUs or consumer-grade gaming GPUs. And within ROCm, you'll see a couple acronyms, HIP or HIP. HIP is the API for writing lower-level GPU accelerated code. Think of it as similar to programming in CUDA. This also lets you port over your CUDA code over to the HIP platform. So another acronym is RCCL, or what we call RCCL. So RCCL is part of the ROCm software stack, and this is the layer that handles collective communications across multiple GPUs. So this happens between GPUs in a single server or even across multiple servers. And these collective communications are just operations that power your machine learning frameworks and allow for parallel tensor operations like broadcast, all gather, and all reduce. So wrapping up, all your favorite machine learning frameworks work out of the box on AMD. You can build and run deep speed code, PyTorch, JAX code, all without having to worry about anything AMD specific while running this. And the frameworks take care of the lower level GPU details when you install them. With AMD support, this is just a pip install, and you pull the package that was built for AMD, or if you prefer, you can just pull down a container instance from our AMD Infinity Hub, and this hosts the latest and greatest Docker images with the ROCm software stack and the frameworks that you're going to use for pre-training or inference. So let's talk at a high level about the hardware and software for scaling out these designs when you run some intense GPU workloads. Large models are typically more than 1 billion parameters these days. This won't fit inside of a single GPU. In addition to that, pre-training your own model on frameworks like PyTorch, you'll most often want to use more than a single server or more than a single instance, just for the additional horsepower and the additional GPU VRAM footprint. So you'll often see pre-training run not only across multiple GPUs in a server, but across multiple servers with multiple GPUs. Because we're communicating across multiple servers, we're gonna need a fast RDMA network to run our RICL collectives and also sync gradients while we run our pre-training across GPUs. Traditionally, this networking was based around InfiniBand, but lately the industry is also adopting RDMA over converged Ethernet or ROCm, just for better economies of scale for teams that already manage Ethernet networks. So not only do we need the fast RDMA network across servers, but we also need internal connectivity. We mentioned the MI300X, our latest GPU, has 8 logical GPUs within the OS. Each of these 8 GPUs uses an XGMI high-speed interconnect to push data in between the 8 GPUs. The XGMI networking is faster than just a traditional PCIe lane. So these are high bandwidth, low latency inter-server connects that power GPU communications inside of a server, and then the RDMA network moves data in between servers. So flipping over to the software side, scaling these workloads for pre-training involves a couple different things. For on-prem, building out these clusters, you'll have a choice, again, of InfiniBand or Ethernet. If you decide to use Ethernet, then you'll need a network design for your switches, and we'll also need to implement this design using the switch software that comes with your switching hardware. So some common switch designs that we see for pre-training are things like fat tree or rail network architecture. We're not going to talk about network architectures today, but these are things you definitely want to consider to scale out, and you also want to follow your switch vendors' best practices for kind of AI traffic flows. You also want to consider your Linux operating system config, because you're going to have multiple RDMA NICs. We mentioned, again, each MI300X is 8 GPUs, so that means we need 8 RDMA NICs in the Linux host, and each NIC needs the software and driver configs within each host within our cluster. And finally, moving up the stack to the ROCm layer, which is the AMD software layer, we mentioned RICL. That's the piece of the ROCm stack that handles collectives over multiple GPUs. This is within a single server or across multiple servers. So to scale, we really need to depend on RICL to split workloads and run parallel tensor operations across our cluster. And finally, when you build out your code to take advantage of a cluster, you'll need to implement machine learning framework APIs that will take advantage of multiple GPUs, multiple hosts. There's techniques that are adopted for spreading the data and the compute across GPUs. Some of these are built into PyTorch, some of them are in frameworks like DeepSpeed Megatron, and these are things like data parallel, model parallel, and pipeline parallel. So these are really the foundational elements that you'll need to consider when you scale out things like pre-training or even inference. And you can build this out in your own data center, or if you want to kind of offload a lot of this on Microsoft, you can just spin these up in Azure. And the Azure instances will have the InfiniBand networking and the host configs already built in. Okay, so for the session today, I pre-trained a GPT-2 model from scratch on an AMD GPU cluster. Really what I wanted to do was show what was possible with just a few servers, and hopefully kind of inspire folks to take a look at possibly pre-training models of your own. My setup is really straightforward. I've just got a couple servers. I've got AMD dual socket EPYC CPUs, and I've got 2 terabytes of system RAM on each host. Each host has MI250 GPUs. These are our last generation of GPU, and they each run with 68 gigabytes of VRAM each. I'm using a back-end network of 200 gigabit ROCm, which is RDMA over Ethernet. I'm using ROCm 5.7 and PyTorch 2.0 installed with AMD ROCm support. So looking at our model architecture, I'm using the open source Nano GPT repo. Folks probably have seen that before. This out of the box will work with AMD and will also support multiple GPUs and multiple servers. Within the configs in the Nano GPT repo, I'm able to train small, medium, and large GPT-2 model architecture, a large being up to 774 million parameters. So this comes with the repo. It also works with PyTorch DDP, which is just distributed data parallel. This puts a replica of the model on every GPU in the cluster and uses that RDMA network to move traffic between the GPUs. So when I did run the training, I tried to stick mostly with the default parameters in the Nano GPT repo. I'm only adjusting the gradient accumulation just so I can kind of experiment with some of the loss values. Gradient accumulation is just a parameter that you can adjust in the Nano GPT repo. This helps you simulate larger batch sizes without necessarily using a lot of VRAM on your GPUs. So the data I'm training on is the Open Web Text open source data set. This is also included in the Nano GPT repo. You can download and compress this down into a 17 gigabyte training file that has 9 billion tokens. So I really wanted to just get a decent sized data set so that we're not just working with a couple of megabytes. You know, this is more of a real world workload when I go to train my models. So to run this across all my nodes in my cluster, I just use the PyTorch torch run command. And on every host, I just use an argument for the node rank to be unique for every server in the cluster. In the HPC world, this is typically done with Slurm to kick this off and manage the job running on a GPU cluster. We have a sample Slurm script in the repo. We'll show a link to that at the end of the presentation. This will just give you an idea of how to use Slurm to manage a clustered pre-training job on multiple GPUs, multiple servers. So this is my setup. Again, GPT-2, adjusting the model sizes. I'm just using a few servers. I'm using the MI250 AMD GPUs, which are our last generation. I'm using the Open Web Text dataset, and I'm using the Nano GPT repo, which is in turn using PyTorch DDP to run the training across my entire cluster. All right, so what does this look like in action? So after I submit the torch run to all my nodes, you'll see this kind of console info when monitoring the job. So in this demo, I'm using 4 servers, each with 8 GPUs. So the job was submitted with Slurm. And on the left side, you'll see the training job showing the loss every iteration, and then every 1,000 steps, it measures the validation loss on the validation data set. On the right, I just have a couple TMUX windows showing the GPU monitoring. So in this run, I had a large GPT-2 model. The GPUs are running at 100%, and I'm using almost all of the VRAM. The Nano GPT code takes care of all this. It also writes a model checkpoint every 1,000 steps out to your shared storage. So here, our goal is to get the validation loss as low as possible. Hopefully something between 2.5 and 3, just based on the GPT-2 model architecture. And typically we would adjust parameters and kind of experiment so that we could get a value as low as possible, minimizing our validation loss. Okay, so how did we do across some experiments? I'll just take a few minutes to show a couple things I ran across the cluster. I decided to just keep my iterations fixed at 10,000, so I didn't run this for all that long. And I just adjusted the number of servers just to see if more hardware, if I could throw more hardware at this problem and get a better loss over a fixed number of iterations. So here I'm using a small GPT-2 model. I'm using 124 million parameters. And on the left side, the upper left, you can see I'm changing the number of GPUs, which is really just the number of servers participating in this. So I'm using 1, 2, and 3 servers, which just means 8, 16, and 24 GPUs. And the gradient accumulation is just set to the number of GPUs in each experiment. So the top left shows the training loss over 10,000 iterations. And on the bottom left, we can see that the lowest loss I could get was with the 24 GPUs. And I got the validation loss down to about 3.3. So more servers and more GPUs over a fixed number of training runs is definitely going to give me the best validation loss. And this is seeing more data because a bigger footprint, and it's just training on more tokens. So on the right side, just for sake of experimentation, I changed the gradient accumulation, kept everything else the same, just to see if I could get a better loss value across my 3 servers. Again, this lets me simulate a larger batch size without really taking a lot more VRAM. Hopefully I can stabilize my training and get a lower loss value. So the top right shows training loss across 1,000 iterations, and I'm using a gradient accumulation equal to 3 times the number of GPUs. So the 24 GPU setup, again, is the best performing. So you'll see on the lower right-hand side, I was able to get this to about a 3.1 validation loss over the 10,000 iterations. So this might seem small, but even small improvements to the validation loss gives me a more accurate and more reliable model that can generalize better on data that it hasn't been trained on. So scaling up with more GPUs and just tweaking the gradient accumulation, they're important, and I'm able to build a better model over a fixed number of iterations. And again, just keeping the number of iterations the same it just makes this exercise a little bit easier to experiment with. Okay, so the last kind of sets of graphs I'm going to show is just how low can I get my loss with the same setup. So my goal here was to get a loss lower than 3 before I hand it off to Databricks for fine-tuning. So to do this, I increased my model size to get a more powerful model. I moved this up to a GPT-2 large model, which is 774 million parameters. And this is about the biggest I can get with my memory footprint of 68 gig on each of my GPUs. And this is about as big as I can get using the NanoGPT repo and PyTorch DDP. Going to a larger model size, over 1 billion parameters would mean I'd have to pivot to something like DeepSpeed in order to kind of split up the model across multiple GPUs. So I bumped up the model size and set the gradient accumulation just to be 3 times the number of GPUs. So in this case, it's 72. I'm just using the 3 server setup here. And you can see I can start to get a training loss here below that goal of 3. And I was able to get a validation loss below 3. So that was my threshold. Again, just keeping that static number of iterations. So there's a lot I could also play with here. There's a lot of parameters we can tune. But I just wanted to show that kind of with minimal effort, just a handful of servers, I was able to build kind of a passable GPT-2 model with less than 1 billion parameters and a validation loss below 3. So hopefully you can see this would be pretty easy to reproduce a couple servers in your data center, or even just spinning up a couple Azure instances with the AMD MI300X. Okay, so I trained a GPT-2 model from scratch, less than 1 billion parameters, handful of servers. The next step is to move this out of my GPU cluster and into Databricks so I can start doing some fine-tuning and some inference. So how do we move this? Just for context, on the left side, you'll see the training data I use. So again, it's 9 billion tokens, 17 gigabyte train.bin file. And then my final model checkpoint file is on the right 8.7 gigabytes. That's the 774 million parameter GPT-2 model. So the next step is to get this 9 gigabyte file out of my GPU cluster and into Databricks. And Avi's going to take you through kind of setting up this model, getting it off the cluster into Databricks so that you can start fine-tuning it and then eventually host it for our applications.
All right, so I'm gonna present. Thank you. So when it comes to moving a model to Databricks, there are like Databricks native approaches and there are non-native approaches. The easiest thing to do would be to kind of upload the model to something like the Hugging Face Hub as a private repo, if you want to keep it private, which I assume you do, because it's based on your data, and it's an artifact derived from your data. Then you can pull it down to the Databricks environment because transformers, the Hugging Face library comes pre-installed. But there's nothing special about that when doing it with Databricks. Another approach that you could do is that if there's a way to kind of shard the model weights, basically like break it up into smaller chunks, you could upload it into a volume, then kind of use Databricks to kind of log the model as a MLflow model on one workspace, assuming that you have access to that from your local cluster. Then you could use a Unity catalog capability called model sharing to move it within kind of the data within Databricks or among Databricks workspaces. Another approach that I kind of wanted to highlight is something that we tried before model sharing was available, so I thought it was kind of fun to break it down. And this is kind of kludgy, but it's kind of worth showing. Now, assuming that you shard the model into pieces, you could these are kind of binary large objects. You could kind of convert that into a base 64 encoded string, stick it in several rows of a delta table, and you could move the delta table around. And this is something that we've tried, and it's worked. But of course, I would recommend that you stick to model sharing that we have as a native feature within Databricks. And the process of moving data with Unity Catalog, model sharing is quite seamless, and it's tightly integrated with MLflow. So the process of fine-tuning models is fairly much less resource intensive compared to pre-training models. So even to pre-train something as small as GPT-2 large, which is less than 1 billion parameters, you had to use a few dozen kind of GPUs. For fine-tuning, there are more options because the amount of data that you're using to fine-tune is far smaller. The number of tokens in a production scenario, Keith used 9 billion tokens to pre-train the model. If you look at data sets like FineWeb or FineWeb EDU, you easily cross 1 trillion tokens. But when it comes to fine-tuning, it's I think several billion would be like an accurate assessment, maybe even less. And the number of samples that you need to fine-tune is typically less as well. Now, when it comes to fine-tuning a large language model, people conflate that with there's multiple aspects of fine-tuning large language models. So if you're fine-tuning, say, a large encoder model, say, like imagine a bigger version of BERT, the process of fine-tuning that for a specific downstream task is quite different from fine-tuning a decoder-only model like Keith just trained, or trained like in preparation for the talk. So you would do what we call supervised fine-tuning for following instructions. So in this case, I am assuming that you're trying to do this in the most resource-efficient manner, and you would use something like LoRa or QLoRa. And even if you have a T4, NVIDIA T4 or the equivalent in AMD with the 24 gigabytes of VRAM, you could fine-tune it on as much data as you want quite easily. Typically, the amount of samples that we use for fine-tuning is fairly small. It ranges in the tens of thousands. For example, $15K, which is one of the first openly available, good to use supervised instruction following kind of data sets, was 15,000 samples. And I think Messiah ML combined that with Anthropic helpful, harmful data set and had an instruction following supervised fine-tuning data set with a little more than 50,000 samples, if I recall correctly. And the process of doing this with a resource-efficient method like LoRa, as I'm showing here, or low-rank adaptation, is quite easy. You essentially have to define certain parameters for fine-tuning. Some of the most important ones are the target, the modules that you want to target in the model architecture. Typically, I've seen the projection matrices being targeted in the low-rank adaptation, but to get more useful, high-quality fine-tunes, you want to target like the attention matrices or the attention projection matrices and the linear layers as well. And if you use something like TRL from Hugging Face and use the supervised fine-tuning trainer, it's like 5 lines of code. But one thing to understand here is that LoRa is easy, but it's not without faults. So if you want the model to memorize certain things, this is not the best way to do it. You would want to go for full fine-tuning. So imagine if you want to do fine-tuning for form, you would do LoRa. If you want to do like memorization and form, you would do full fine-tuning. Speaking of full fine-tuning, if you were there at the presentation that we had in the morning with the keynotes and things like that, Patrick and Casey highlighted some of the capabilities that we are releasing. We have already released and kind of rolling out now. One will be the fine-tuning API. You don't have to really specify that many parameters. You have to point it to the data, and you just do the fine-tuning. And there's a SDK for it. There's also going to be a user interface for kind of seamless doing this. You just point it to the data, you run it, everything runs in a serverless manner. So it's a Mosaic AI feature that's quite seamless and easy to use. So there are customers who are already using this in certain contexts, and we've seen some good results. And since I'm in the MLflow team, I want to highlight that this is fully integrated with MLflow, just like everything else on Databricks, including model sharing and so forth. So everything that you do here is going to be tracked and logged and governed by kind of the MLflow set of capabilities that you have access to within Databricks. Another thing I'm really interested in is that when we started doing this fine-tuning stuff on Databricks, we had to like do a lot of, not a lot of, but like run some shell scripts to understand like what the system metrics look like in terms of GPU utilization and kind of essentially understanding where certain bottlenecks were in the training run. But with the recent, or a couple of months ago, we introduced system metrics as a part of MLflow, and this has been a much well-received capability within MLflow for fine-tuning or not just large language model workloads, but other deep learning workloads when you're using kind of specialized hardware like GPUs. And of course, we've done a lot of releases for MLflow over the past few months to kind of monitor training runs better. And as a matter of fact, I believe that the Mosaic team used MLflow a fair bit for DBRX, where they had used weights and biases before for that. So the same capabilities are available within the platform for Databricks end users to utilize. Now, when it comes to model serving, you have several options. And the most obvious one for the model that we just trained, or Keith just trained, would be to use GPU model serving, which is serverless. The reason I'm kind of proposing this as opposed to the other serving offerings that we have is that GPT-2 is an older model architecture. Everybody uses it to teach machine learning and kind of run, like POCs and things like that. It's like a classic machine learning model or deep learning model, but nobody really uses it for actual production use cases anymore. But since it's a custom architecture in the eyes of like most serving services, we have to deploy it as a custom model. And for that, GPU serving is perfect. It's serverless, and you can serve as something as complex as a vision language model, or you can serve as something as simple as adding two tensors together because it's an arbitrary GPU-bound function. So you could think of this as serverless functions for machine learning utilizing GPUs. And of course, there's nuances to this, like with the whole large language model ecosystem. There's an opportunity to kind of wrap these models in kind of language, kind of LLM chains. There are other more involved architectures like diffusion models where you have a unit, kind of a text encoder, an encoder and a kind of an autoencoder portions that's kind of all lumped together. You can deploy any of these within using model serving on Databricks. Now, had we fine-tuned or pre-trained something like Llama 7B, which is a much more sizable model, which we would have used to use FSDP, fully sharded data parallel for, we could have deployed using foundation model APIs. There are two options for that. If you want to use something that comes out of the box and get charged per token, just like you would get charged by a model provider like OpenAI or Anthropic, you can easily use the paper token option for the foundation model API. And we have the latest open source models that are popular, available. For example, Llama 3, DBRX, and so forth. And once you get done with a POC that uses this kind of paper token thing, you would want certain tight SLAs for your production applications. So we would definitely recommend considering provision throughput. So you get dedicated compute, essentially a privately hosted foundation model that's kind of optimized for production use cases. So if you have, I'm assuming that if you're putting something in production, you have tight SLAs or certain requirements. This is a much more recommended route. So when it comes to custom model deployment, you have several options, as I mentioned. Another thing that you could also do is like kind of choose although this is serverless, you have some choice when it comes to like the amount of memory required. So if you're deploying a small large language model, which sounds, I don't know, it's an oxymoron, I guess. If it's a 1 billion parameters, it's still a large model, but it's a small large language model. You could go for a smaller GPU instance, and you could have much larger models served using the same mechanism, especially when it comes to vision language models and things of that nature. You would want a larger GPU to kind of like enough VRAM to support it. In terms of kind of other capabilities, there's a lot in here. For example, kind of horizontal scaling, and kind of you can turn the endpoint off when there's no traffic, things like that, and you can split the traffic between multiple endpoints, things like this. So this is super helpful for custom model deployment. The reason that this is also useful is that most machine learning systems or large language model-based systems that you build are not going to be just using a foundation model API. There's going to be other components. So if you want to have for document intelligence, you want to have a layout LM2 or something like that deployed. This is a good mechanism to deploy that. So for the fine-tuning part using QLoRa, I decided to go easy on the GPT-2 model because, again, it's a very kind of proto ChatGPT model in that it came way before all the cool stuff came out. So I decided to fine-tune it with just the IMDb dataset so it can generate coherent movie reviews. And that dataset has like 50,000 samples. So the process of fine-tuning that on Databricks, even without any of the fine-tuning API, it took me like 10 minutes I think it was on an A10 or something like that. And once you deploy that with model serving, you essentially roll it into a PyFunc, which is a custom class in MLflow. Then you can, within like a couple of clicks, you can deploy it into a GPU serving endpoint. You can kind of see, I can interactively generate descriptions and things of that nature using custom prompts. Then I can get the corresponding code, whether it's curl command or Python, or if you want to call this within SQL, you can get that code and run it, integrate with the application. Since it was movie reviews, I call it Happy Ebert, the homage to Robert Ebert, if you know who that is. It's like an old movie critic that's not there anymore, but it's kind of funny. But the idea is that the same mechanism, the same customer user journey could be used for fine-tuning much larger models, especially if you're talking about like pre-training, that something that follows a Llama 3 7B architecture. You can fine-tune with the fine-tuning API, or if you want to have a custom pre-trained model, whether you pre-train it yourself or use the Mosaic hero runs, you could follow the same path to put that model in production, essentially, using a very reliable set of choices. So that's all I had to share in terms of how you could take this from pre-training on using services and hardware of your choice, whether it's AMD or something else, to deploying that within Databricks and integrating with the applications. As far as the summary is concerned, so we showed.
Yeah. So combine AMD and Databricks platform. So if you're going to look at a GPU-intensive workload, AMD is ready to go. All your frameworks will work. If you're interested in running this in Azure instead, look for the ND MI300X V5. That's the latest and greatest. And to scale this up, you have to definitely consider your RDMA network and your interconnects so that you've got fast data movement, high bandwidth, low latency between servers and across GPUs, and work within your model framework to build out code that will take advantage of everything. And the next best step is move it out to Databricks, do your fine tuning, and run your inference on a platform that'll make everyone more productive. And Avi's got some code up on GitHub, and I've got a Slurm script up there in case you're interested. And it'll show you how you can run this across a cluster and kind of manage the job in an HPC-friendly type way.
Thank you.
Yeah, thank you.